Okay, good morning and welcome to today's class. So let's continue what we left off last time. So last time we were talking about uh, energy density spectral. Okay, the concept of energy density spectral is based on Parseval's theorem, and Parseval's theorem states that the area under the magnitude square of the time domain signal is equal to the area of the magnitude square of the spectrum of the same uh, signal divided by 2 pi. So this is equal. Okay, this equation is called Parseval theorem. Now we recognize that the left-hand side of the equation, this term, this integral, is simply the energy of the signal. Okay, we've talked about this in chapter 1 extensively, so this is recognized as the energy of the signal. So Parseval theorem basically states that we can find the energy of a signal, okay, either using the time domain signal, the area under x squared integrated over time, or we can find the energy of a signal using its spectrum squared here. So this is basically what Parseval theorem tells us. So so we so so says that we can find the energy contained in a signal xt by ex, right, is equal to 1 over 2 pi integrated from minus infinity to infinity the magnitude of the spectrum of x squared, and the integral is with respect to the frequency. So this is what Parseval theorem tells us. Now, um, from this equation, okay, it is quite useful to think about the integrand here. Okay, this integrand is a function of omega, right? And we are integrating this integrand over the entire frequency. So let us define what we call energy spectral density function, the energy spectral density of the signal x as big E, right, at x, and it is a function of omega. Okay, this function is defined as the energy spectral density. So it is defined as 1 over 2 pi, the magnitude of x squared. So this is the energy spectral density function, and it is defined for all frequencies. Okay, it is defined for all frequencies, either negative frequency or positive frequency. So using this definition, uh, we can conclude that the energy of a signal X can be obtained by finding the area under curve of the energy spectral density. Okay, so in other words, if we are given the energy spectral density of a signal, we can find the energy of the signal by integrating this function over the entire frequency range. All right. Now, we note that if the signal x is a time-valued signal, when xt, I'm sorry, is a real valued signal, is a real valued signal. Okay, the value of x is a real number. Okay, then it can be shown quite easily that it can be shown that the magnitude square of the spectrum of x is an even function. Okay, this is an even function. It can be shown that this is an even function. So that means the energy spectral density of a real valued signal is also an even function. So, so the capital E of x is an even function, right? Even function of frequency. So the energy of x, which is equal to integrating the energy spectral density over the entire frequency, could just be determined by integrating over the positive frequency only and multiplied by 2. Okay. So this leads us to another definition of the energy spectral density. So we can define the energy the positive frequency, okay, the positive uh, energy spectral density as this. So we can define the positive energy spectral density as E of x plus, okay, the symbol plus here indicates that this is defined only for positive frequencies. So this is defined as a 1 over pi and absolute value of x of omega squared. But now here in this definition, the frequency is non-negative. Okay, so we have two definitions there. We have one definition is the general, is the energy spectral density defined for all frequencies. Okay, and the other is defined only for positive frequencies. But when we have to define for a positive frequency, right, we have to multiply by 2. Okay, we need multiply the the energy spectral density, the original frequency spectral density by 2. Okay, because of the even characteristics of the EX there. So this is only defined for only the positive frequencies. So I'm going to give you an example. So so the energy of X here is if we're using EX, the both sides frequency, we can integrate it over all frequency, or we can use the positive energy spectral density. But if we use EX plus, we have to integrate just only over the positive frequency range. All right. So example, rectangular pulse, rectangular pulse. Okay, do you remember what a rectangular pulse is? A rectangular pulse is a signal defined by a rectangular function, a rectangular variable t over the constant t here. Now, if you don't remember, okay, it is a box. It looks like a box, and the width of the box is capital T. And the height of the box is A. So this is our signal X, a rectangular pulse signal. Now, I'm going to find the energy spectral density of a rectangular pulse signal. Now, before I do that, I need to find the Fourier transform of the signal, right? So we know that the Fourier transform of X, we take the Fourier transform of both sides of this equation. On the left-hand side, I'm going to get x of omega. And on the right-hand side, I'm going to get the Fourier transform of A, rectangular, small t over big T. And I know I can pull the constant A out of the Fourier transform. So I'm going to get Fourier transform of rectangular, small t over big T. And I know that we've done this before. The Fourier transform of a rectangular signal is just the sinc function, right? It's just the sinc function. So it is A t sinc of omega t over 2. So this is the spectrum of the rectangular pulse. Now, so the energy spectral density both sided, it is 1 over 2 pi. The absolute value, the magnitude of the spectrum squared. And it is going to be equal to A squared T squared over 2 pi, and then sinc squared omega t over 2. So this is both-sided, defined for all frequencies. And the one-sided version, as for the one-sided version, defined only for positive frequencies, it is 1 over pi absolute x squared. So it's going to be a squared t squared over pi. And sinc squared omega t over 2. But now we have to indicate that it is defined only for positive frequencies only. Okay, so these two are the energy spectral density of a rectangular pulse signal, right? The top one is both sided, defined for all, either negative, both negative and positive frequencies, and the bottom one is defined only for the positive frequencies only. It is one-sided and both-sided. Now, if I attempt to plot the graph, it would be here. Okay, it would be it looks like this. This is a graph of zinc square, right? And the zero crossing occurs whenever the inside of the parentheses is um, k pi, right? So the first zero crossing occurs at omega equal to 2 pi over t. So this is 2 pi over t, and the second zero crossing occurs at 4 pi over t, twice that. And the third is 6 pi over t. And notice that this is an even function, right? This is an even function. And this is minus 2 pi over t, minus 4 pi over t, minus 6 pi over t. Okay, and the maximum value occurs at omega equal to 0, and that is a squared t squared over 2 pi. And this is a both-sided ESD. This is the both-sided ESD. Now let's try to let's try to plot the one-sided ESD. Okay. For one-sided ESD, right, I have to indicate it using the positive sign there, and I'm gonna have to erase the 2 there. Okay, the factor 2 would be erased. And I know that it is defined only for positive frequencies, right? So I'm going to erase the negative parts out of the picture. Ooh. Here. All right. And then for negative frequency, it is 0. Right. Actually, the height of the lower graph is twice the height of the upper graph. Right? But it is actually higher. The height is higher. So, yeah. Notice here, we don't have a factor 2 in the bottom, okay? Whereas the both-sided version, we have a factor 2 in the bottom. So this indicates that the height here in the lower graph is actually twice the height of the upper graph, okay? The graph is not scaled, so it could be misleading. So that I want you to notice, take a note of this. Now, now, um, from the from the definition of E, right? From Ex equal to integrating minus infinity to infinity Ex omega. Now, the unit of energy is of course joules, right? Unit of Ex is joules. The unit of this guy is joules, and the unit of omega is radians per second. So what would be the unit of the ESD here? The unit of ESD here has to be, if we multiply the unit of this guy, it's this function, by radians per second, the result would have to be joules, right? So the unit of the ESD would have to be joules per radians per second. We notice that EX has a unit of joules per radians per second. So this indicates that it is actually a density of energy distributed across the frequency range. Okay, this function, sorry, this function is actually the distribution of energy of the signal X across the entire frequency. Okay, so because of that of the unit there, right? Joules per radians per second. So the ESD will indicate the distribution of energy of X within uh, across the frequency spectrum. That means that the energy, the area of this means that the area of EFX over an interval I. Okay, if the area of Ex over this interval I will just be the energy of the signal X that is contained within the frequencies range of I here will be the frequency, the energy of X that is contained within the frequency interval I. And that is, so this is what I mean. What I mean is that if we integrate E of X plus d omega, the result from the integration would be equal to the energy of the signal X that is contained in the interval I. Of course, this is not the entire frequency. This is not the total frequency. This is the partial energy. The total energy would have to be the energy contained across all the frequencies. So if you pick some interval out of the entire frequency and integrate Ex over that interval, that is going to be the partial energy that is contained only in that interval. Okay, right, so the energy of X contained within interval Okay. All right. Uh, so if we take a look at this graph, okay, this is the graph of the ESD of a rectangular pulse. We see that, look at this graph here. You see the area under this graph over interval starting from 0 to 2 pi over t is considerably larger than the areas of the rest of the interval, right? The area here, if you look at this, the area here is very, very large compared to the rest. So this means that for rectangular poles, most of the energy is contained within the frequency starting from 0 to 2 pi over t, okay? Because the area here, relative to the other area, is very, very large, okay? So if we look at the graph of Ex plus one-sided for a rectangular pulse earlier, we see that most of the energy of X rectangular pulse, I mean, is contained, oops, sorry, within the interval 0 and 2 pi over t. Okay, so it is basically a low frequency signal, right? Low frequency signal. In other words, if frequency is higher than 2 pi over t, then we can expect that the energy is not very large. So we can practically eliminate those part of the frequencies without any much consequence. Okay, we can just only consider the signal in this interval, in the frequency interval, right? Because most of the energy of the signal is contained in this interval. Okay. Right. Another example, um, let x of omega, I'm sorry, let e of x plus the one-sided be shown below. So suppose that we have a signal whose one-sided energy spectral density is given here. Suppose it is a kind of like a triangular shaped signal there. Let's just say that this is one, this is b. Okay, this is e x plus. Okay. Now we want to find the energy of the signal. We also want to find the value, find the frequency omega 0 for which uh, such that the energy that is in the interval from 0 to omega 0 Ex plus omega is equal to 1/2 of the total energy. So in other words, we would like, in part B here, we would like to locate a point on the horizontal axis so that the area is half the total area. Okay, we would like to find that frequency for which the energy is half of the total energy. Now to answer that, let's find the total energy first. The total energy is easy to find because we just only have to find the area under this curve, right? We know that the total energy is equal to the area integrating that function over the positive frequency, right? So Ex is integrating from 0 to infinity, one-sided ESD, and integrating this function is just the area of the triangle there. So it is 1/2. We don't have to integrate, right? 1/2 times the base, which is b, times the height, which is 1. So the energy would be b over 2, or 0.5 b. Okay, that's easy. Now for part B, we want to find omega 0. Now we have 0 to omega 0. Okay, and the graph here is a linear graph, right? The slope of this is minus 1 over b. So minus omega over b, and the y-intercept is 1. The omega, we know that we want this to be 1/2 of Ex. So what is this? What is this integrand? This integrand represents the linear line here, the straight line here. This is a straight line. The slope, this is minus 1 over b, right? Minus 1 over b, and the y-intercept is 1, so I write down 1 there, and I have to integrate it from 0 to omega 0, somewhere here, such that the area, the integral would be 1/2 of the total area, which is the energy. That is what is required for us to do, right? So the right hand side is easy. We can just plug in the value that we just found. So this is going to be equal to b over 4, right? We could plug in b over 2 here to Ex, and the result would be b over 4. Now what about the left hand side? The left hand side would be minus omega squared over 2b and plus omega, right? Where omega ranges from 0 to omega 0. And that has to be equal to b over 4. Okay, and then we can plug in the upper boundary, right? Because the lower boundary is 0, so that would give us nothing. Okay, we could simply ignore the lower boundary because it's 0. So plugging in omega 0, we have omega 0 squared over 2b plus omega 0 equal to b over 4. And this is just a quadratic equation, right? We can multiply through by 2b. Okay, multiply by 2b, and we're going to get minus omega 0 squared plus 2b omega 0 equal to a b squared over 2. Okay, and then we have omega squared minus 2b omega, and then plus b squared over 2 equal to 0. Okay, and we can do the perfect square, right? Omega 0 minus um, minus b, right? Squared, and then plus b squared over 2, and then minus b squared equal to 0. And so this is just omega 0 minus b squared minus b squared minus ah, minus b squared over 2, right? Yeah, b squared over 2 equal to 0. So we have omega 0 minus b over 2, and omega 0 minus b plus b over 2. Actually, I don't have to do this, right? Uh, okay, this is square root of b over square root of 2. So, but this is, of course, out of range, right? So we have this. So this means that omega 0 is equal to b minus b over square root of 2. So square root of 2 minus 1 b over square root of 2. Okay. Actually, you know what? I could use the quadratic formula, right? This might be easier. I think I have to erase this one. Okay. The formula is much easier to use. This is much easier. So this is equal to b plus minus b square root of 2 over 2, right? Yeah. So b 1 plus minus 1 over square root of 2. So b, so it is square root of 2 plus minus 1 over square root of 2 and b, right? But we have to use the minus value, right? Because the plus value would have to be, it is greater than b, and that is not acceptable because b, omega 0 would have to be less than b, right? It has to be somewhere here, less than b. It cannot be greater than b, right? It has to be less than b, so we have to use the lower value. So this means that the value, the frequency value we're looking for is square root of 1 minus 1 over square root of 2b. Okay. So let's calculate this. I think it is about 1 minus 0.707, and that is 0.293. So about 0.3b. It is about 30% of the bandwidth of b. Let's see. Yeah, about 0.3. Okay, so what this means is that if the ESD, if the energy spectral density is this shape, then at this frequency, at point 3, the maximum frequency, at this frequency, we can expect the energy to be half of the total energy. So this is half of the total energy. Of energy. All right. Okay. So this concludes this chapter of Fourier transforms. So if you look at the last example, do you have any questions about this one? No? Okay. If there are no questions, I would like to move on to the next chapter because we are running out of time. We don't have enough time. Now, the next chapter is chapter 6. This chapter is about sampling of continuous time signals. CT means continuous time. Okay, we would like to take samples of continuous times because if I am to record my voice onto computers, because computers are digital devices, I could not just record the signals that comes out of the microphone to the computer. It doesn't work like that. So what I have to do is I have to kind of like digitize. I have to digitize my voice signals because my voice signal is an analog signal and continuous time signal. Okay, so I have to digitize it. Now the process of digitizing my voice has to begin with sampling of my voice signals. Okay, sampling means converting from continuous time signals into discrete time signals. Okay, sampling. So sampling means process of getting a discrete time. DT means discrete time signal out of a given continuous time signal. So how do we do this? All right. We have a continuous time signal xt coming in. Okay, we could do this sampling thing by feeding it into a switch. Okay, we have a switch here, and this switch is like oscillating. Okay, it is closing for some amount of time, and then it opens, and then it closes, and then it opens, continued forever. So this switch closes every ts unit times, let's say seconds. Okay, the switch closes every ts seconds. So what we have at the output of this process is we have xs t. Okay, now if we're gonna assume that the amount of time, the duration over which this switch is closed is very, very small, we assume that the, the closing period of the switch is very small. Okay, so what we have would be if we have a signal x versus time coming in like this. Suppose we have x coming in and the signal is something here. Okay, some arbitrary shape, and let's denote the frequency period, the sampling period. Ts, 2ts, 3ts, 4ts, 5ts, and so on. And this minus ts, minus 2ts, minus 3ts. Now, under the above assumptions, then xs would be this, right? This is the xs. Now, these are the xs. Let me highlight it here. The green bars are the xs. You see, they occur at discrete time intervals. They occur at discrete times. Okay, every ts seconds, the value of xs appears every ts seconds. So if we from this picture, if we erase the blue line, look careful, I'm going to erase the blue line. Then this is going to be the xs. This is going to be this signal, the sample signal. You got that, right? Let me erase this one first. I don't think I need this. I don't think I need the blue shades. Now the blue lines, the blue bars are the xs. So let me indicate that here. Oops, sorry. xs. xst are the blue lines. So if I erase the blue, the orange line, if I erase the blue lines, this is the signal xs. Right? This is discrete time signal version of the original one that I just erased, right? Okay. You understand what I'm saying? So this is xs, okay? And the blue line is x. The xs is the discrete time version that is sampling, that is sampled of every ts second. So this is what I mean by this process. Okay. Now we are now trying to find. We're now trying to find, do the analysis of trying to find the spectrum of this signal. Okay, so we're trying to find, now we're trying to find the spectrum of xs. The question is, given the spectrum of x, what is xs omega. Okay, we try to find the spectrum of xs, the spectrum of the sample signal. Now, how do we do that? To find xs, okay, we use, we start with xt. So the question might be, what should we write? What should we represent xst? Okay, xst, the sample signal in the time domain. Now, xst is a sampled version of xs every ts seconds. So it is reasonable to write xst as xt, right? xt multiplied by the impulse train, okay, multiplied by the impulse train that are the impulses are ts apart. Okay, you remember this impulse train, right? This is the impulse train. Okay, let me draw that for you. So this is the impulse train I'm talking about. Impulse train. This is the impulse train. The spacing is Ts. Okay, Ts, 2Ts, 0, minus Ts, minus 2Ts, and so on. This is the impulse train. So it is reasonable to say that if we multiply the blue line here, if we multiply the blue graph here with this impulse train, then we're going to get the sample signal, xs. Okay, we are multiplying this one with the blue graph of x. So that means that we are having this equation. Now, we're going to take the Fourier transform on both sides. So we take the Fourier transform. The left-hand side would be what we're after, which is xs omega. Okay. At the right-hand side is the Fourier transform of the whole thing. So I'm just going to copy and paste the whole thing. Copy and then paste in the whole thing. Now, this is just the product of two signals, right? This is just the product of the two signals. So let me highlight it. The first term is xt, okay, and the other term is this impulse train. So it is a product of these two functions. Now we know that the Fourier transform of time multiplication, we can use the time multiplication property of Fourier transform. Time multiplication property states that if one domain is multiplication, then the other domain would be the convolution. Remember that from last time? Now, this is multiplication in the time domain. So the Fourier transform would have to be the convolution of the spectrums of both, right? But we must not forget to divide it by 1 over 2 pi. So this is going to be x of omega. Okay, and then convolved with the Fourier transform of summation n from minus infinity to infinity delta t minus n ts. Okay. All right. This is from time multiplication property of Fourier transform. Now, we have to think about this one. So what is the Fourier transform of impulse train? I think I've done it somewhere previously. Let me scroll up a little bit and find what I've done. I'm gonna point it out to you that we've seen this earlier. Impulse train, impulse train. Where is the impulse train? No. Ah, here. Yeah. Okay. It is here. This is a Fourier transform of rectangle of periodic signals, right? But now the impulse, this is going to be the Fourier transform of each impulse, and that has to be one, right? It has to be one because an impulse has a Fourier transform of one. So this is going to be one. The generating function of the impulse train is delta, and we know that the spectrum of delta is one. So we know that the Fourier transform of the impulse train is given by this equation, okay, where this term has to be one. So I'm using this and then plugging in to our equation here, plugging into here. When I do that, I'm gonna have 1 over 2 pi x of omega convolved with um, summation k from negative infinity to infinity, and then omega s, and then delta omega minus k omega s. Okay, this doesn't come out of nowhere. Okay, we have proved this already. We have shown. We have seen this already earlier from last time. Now, I'm having this one, so I am noticing that omega s is just 2 pi over ts, right? This is 2 pi over ts. This is 2 pi over ts. So I know that the factor 2 pi will cancel out. So I can pull ts out of the parentheses to the front. So I'm having, oops, so I'm having a 1 over ts, right? Here at the front. And then I can use the distributive property of convolution to bring x omega into the summation, right? From the distributive property, I can bring this x omega inside of the summation, okay? So I get summation k from negative infinity to infinity, right? And then inside would be x of omega, convolved with delta omega minus k omega s. This is from distributive property of convolution. Of convolution. Now, what do we know about this? If I have some function convolved with a delta, right, it means that I'm putting that function at this position. Okay, if this is zero, then the result would be x omega itself. But we are sliding, we are putting delta at this frequency, right? So the result from the convolution would be the signal x slided to this frequency, okay? Position back, the new position of x would be this at this frequency. So the the result from the convolution would be 1 over 2s summation k equal to minus infinity to infinity and x, and I have to replace omega with omega minus k omega s. Remember from chapter 1, right? From chapter 2, actually. From chapter 2, we had any signal, convolved with delta t minus t0, the result will be f of t minus t0. Okay, this is from chapter 2. So we can conclude that the spectrum of the sample signal is given by 1 over Ts summation of k starting from minus infinity to infinity x of omega minus k omega. Now this is a big result. Okay, this is a big result. So I'm gonna box it, put a box around it. And this is important. So how do we interpret this result? So let's look at an example. Suppose we have x of omega given below. Okay, suppose we have x of the spectrum of x that looks like um, something you tell me. So what does it look like? Let me draw it again. Sorry. Suppose the spectrum of the signal that we are trying to sample looks like this, right? And let's mark this one as mark it as B, okay? And this is minus B and 0, and this is A. So let's say that we are given this spectrum and we are sampling this signal every Ts seconds. Okay, we sample xt every Ts time units. So this means that omega here, omega s, is equal to 2 pi over Ts, right? So we're going to have to plot xs that comes out of the sampler. So this graph is the vertical axis is xs. Now let's look at this equation. So what do you see? When k is equal to 0, okay, if you look at the summation here, if k is equal to 0, then all of this is gone, right? So we're going to have x of omega. So when k is equal to 0, then the summation is just x omega itself. So I'm going to draw x of omega here. Okay. Oh. Here. Okay. Now this is when k equal to 0. What about when k equal to 1? When k equal to 1, then it would be x omega minus omega s. So it is going to be x omega shifted to the right by the amount of omega s. So when k is equal to 1, I have this graph. shifted version to the right, right? This is when k equal to 1. This is k equal to 0. Now what about when k equal to 2? When k equal to 2, then I have to shift x of omega by twice the value of omega s, right? So instead of position at 0, I have to position it at 2 times omega s. So I have this when k equal to 2. Okay, this is when k equal to 2. Now, what about when k is negative? When k is negative 1. When k is negative 1, instead of shifting it to the right, now I have to shift it to the left by the amount of omega s as well. And similarly, for k equal to minus omega 2 times omega s. So let's mark the horizontal axis. Of course, this has to be omega s. This has to be twice omega s. This has to be minus omega s. This has to be minus 2 times omega s, right? And then what is this value here? What is this position, this frequency? It would have to be omega s minus b, right? So this is omega s minus b. And this is omega s plus b. Okay? And what about this? This is minus omega s plus b and minus omega s minus b. Okay? Do you see? So this is all the spectrum of the sample signal. Okay, so this is when k equal to minus 1, k equal to minus 2, and so on. It doesn't stop here. It goes on, both to the right and to the left forever. Now I should connect all these guys, right? I should connect these guys together. Yeah. So we started with the spectrum of the signal, original signal, right? We're sampling it every ts seconds, and the sample signal would have. We end up with a sample signal that has a spectrum here, shown here. Now, if you look at this graph, you're going to notice that the assumption that I'm using is that omega s minus b is greater than b, right? Right? Notice here, oops, sorry, it's too big. It's big. Notice here that I am assuming that b is less than omega s minus b, right? I'm assuming that this equation is true because this point, when this condition is true, then this point is located to the right of this point. So the spectrum of X are separated nicely. Okay, we have separated spectrums of X nicely, very nicely. That if this equation is not true, if this condition is not satisfied, then what are you going to have? We're going to have convoluted spectrum, right? They will overlap. Okay, and you will not, actually, we will not be able to understand it because they will convolute it and overlap together. Okay, so this condition says this condition the consequence of this condition is that the spectrums here are separated. Okay, so that the spectrum of X are separated in this. Okay. Now, this comes the next issue. Okay, this comes the next question. If I have, excuse me, I have to scroll up a little bit. So I have to ask, if I have this without knowing this signal, if I know this one without the knowledge of xt, would I be able to retrieve x of t back, knowing only xs? In other words, if I know only the bars, the orange bars here, would I be able to retrieve the blue lines back? Now this is very weird, right? This is very weird. At first, it would be impossible, right? It would be impossible to retrieve the blue line back if we know only the orange lines. Okay, at least how do we know that these values exist? How do we know the values of the line in between, right? We only know the bars, we don't know the blue, and yet we would like to retrieve the blue line out of the orange bars. How do we do that? It is very weird. But it turns out it is possible to get the blue line back, knowing only the orange bars. Knowing only this one, if we know this one, we can get this signal back. It is very weird, right? Now, how do we do that? If you look at this spectrum of xs, okay, and we would like to obtain xt back, the word, the sentence, the statement we would like to obtain xt back means that we would like to obtain this spectrum back, right? Xt is this spectrum. So if I can obtain the spectrum, this spectrum back, then I would know xt, right? So if you look at this graph, how do I get this one back? How do I retrieve this one from this graph? If you look at this graph, then it becomes very easy, right? I would just simply throw away all these side spectrums here. And I would like to filter out and get this one only. Okay, so if somehow if I have this and pass this through something that filter out the lateral spectrums and output only this one, I'm going to have this signal back. Okay, so this answers the question I was posing. So, notice also that if we know xs, right? How do I write it? What should I write it down? We can under this condition, under this assumption, we can get x of omega back, okay, by filtering out all the side spectrums. Okay, so what I need to do is I need to pass xs of t to something, okay, to something, and then I'm gonna have xt back. Then I'm gonna have xt back. So the question I'm asking you, what should be this something? What is this something? What is this box? You've seen it before. So the property of this box is to retain this portion of the spectrum while rejecting all of the higher frequencies. It would have to retain the low frequency spectrum, right? And reject all the higher frequency spectrums. So this box is a low pass filter. Okay, it is actually an ideal low pass filter, right? So I know that if I pass the sample signal through an ideal low pass filter, then I'll be able to get the original signal back, the blue line back. Okay, so this would be the ideal low pass filter. And the cutoff frequency of the low pass filter has to be somewhere here, right? The cutoff frequency of the filter has to be somewhere here so that I can get this signal back. Okay? But all of this is possible. All of this is possible only when this assumption is true. Okay? Only when the spectrums here are not overlapped. If the spectrums here are overlapping, then I would not be able to obtain this one back. Okay, because of the overlapping, right? The spectrums here would have to be separated so that I would be able to get this one back. Okay, so this assumption is crucial. This assumption is crucial. So now, see, this one, x hat is equal to xt only when b is less than omega s minus b, right? So this is a necessary condition. Okay, if this condition is not satisfied, then we will not be able to get xt back. Okay, if this condition is not satisfied, we will not be able to get xt back. So that's why I call it this is a necessary condition. Now, if I rearrange this equation, I would have omega s has to be greater than 2 times b. Okay. So what is b? What is b then? What is the value b? If you look at the graph there, the value b is the maximum frequency of the signal, right? B is the maximum frequency. Any frequency higher than B doesn't contain any x, right, at all, because x is 0. So B is the maximum frequency of the signal x. So that means that the sampling frequency omega s would have to be greater than twice the maximum frequency of the signal if we are to get the original signal back. We would have to sample it with a rate that is at least twice the maximum frequency of the signal that we're sampling. So we need the sampling rate, sampling frequency, omega s to be at least twice the maximum frequency of xt. Now, twice the maximum frequency here, or to be here, is called, there's a name for it. It is very important that we name it. It's called the Nyquist sampling rate. This is called the Nyquist, 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 Nyquist. Uh, Sampling rate. In other words, the sampling rate would have to be greater than the Nyquist sampling rate if we are to be able to get the original signal back by passing it through the ideal low pass filter. Okay? So there are a couple of terms I'd like to address before we go on, before we move on. Notes, a couple of terms you need to know. Okay, first, TS. TS is the sampling period. This is the sampling period. It is the duration between successive samples. Okay, the duration between successive samples, adjacent samples. The second term is Fs. Fs is 1 over Ts, and it is called the sampling rate. The sampling rate. The rate of the sampling. The unit of this is samples per second, samples per unit time. So it is the amount of samples, the number of samples in 1 unit time or in 1 second. Number of samples in a unit time, or if you prefer, in a second. Okay, and the next one is omega s. Okay, that we have been talking about. Omega s is actually 2 pi over Ts, and it's actually 2 pi f. Okay, and this is another. This is the sampling frequency, and the unit is radians per second. Okay, unit is radians per second. So these are a couple of terms that you need to know. Usually, okay, you will see Fs. So usually this parameter is most important, Fs, the sampling rate. Okay, sampling rate. Right. Now, example. Now, suppose xt is cosine of 2 pi 4000 t, okay, plus cosine of 2 pi 3000 t. Now, suppose we are given this signal A, find the Nyquist sampling rate. I'm telling you, this chapter is probably the easiest chapter in the entire course. Okay. If you're if you're going to get some score out of the exam, this would be the perfect chapter to get the score. It is the easiest one. B. Uh, what happens to what happens if the sampling rate is 9,000 samples per second? Oh, I forgot to mention, T is in second. Okay. And C, what happens if Fs is 5,000 samples per second? So we are given the signal there. Okay, it is composed of two sinusoidals, one at 4,000 hertz, the other at 3,000 hertz, right? Now, in part A, we're trying to sample it. Okay, we want to sample it with some sampling period, with some sampling rate. In part A, we would like to, given X, we would like to find the Nyquist sampling rate. So that is easy. Okay, part A. The Nyquist sampling rate is just twice the maximum frequency of the signal, right? Now, if you look at the signal, what would be the maximum frequency? This signal has two frequencies. One at 4,000 hertz. This is the frequency, right? 4,000. The other at 3,000. So the maximum frequency of X would have to be at 4,000, right? This is the higher one, the greater one, 4,000. Okay? So it is 2 times 4,000, and the result would be 8,000 samples per second. So this is the Nyquist sampling rate of this signal. So if we try to sample this signal under this rate, with a rate lower than 8,000, we would have a problem. And that would be in part C of the question. Now in part B, we're sampling it with a rate higher than the Nyquist sampling rate, so that shouldn't be any problem. So let's investigate it. I know about the time. Sorry. So in part B, okay. So let us draw. This is hertz, all right. This is hertz. So x of omega here. X of well. So we have two impulses, right? Because cosine, if you remember, the spectrum of cosine are impulses at two frequencies, positive and negative impulse. This is the spectrum of X. One is at 3,000, 2 pi 3,000. The other is at 2 pi 4,000. So this is 2 pi 4,000. This is 2 pi 3,000. I think I should stop here, actually. I look at the time. I should stop here, and we will continue this next time. If you remember, Uh, I asked you one time that we would need to have a makeup class, right? Because I would we would not be able to finish almost everything because next week's last week of this course. So I would like to ask you a favor to give me one makeup class, and that would be if you're okay. I would like to do a makeup class on Saturday, online. Of course, if you are unable to attend, I would like to. I would be happy to record the clip for you to watch it later. And so, what do you say if we are doing it at 10:30 on Saturday, 10:30 the same time here, 10:30 in the morning on Saturday, this Saturday, online on WebEx. You okay? All right. So we will resume this on Saturday. Okay. Makeup class Saturday. This Saturday is 22nd, right? At 10:30 to 12 o'clock. I appreciate your attendance. If you cannot attend, it's okay. I will not be checking attendance.